8.2, measure of running time. In this part, we will consider a concept, how to measure the running time. Why we do that? Yeah, because we want to do analysis of algorithms. Yeah. All right. So after we develop an algorithm, so the next thing we want to do analysis of an algorithm. But what is the analysis of algorithm? What do we really need to do? Yeah. So here in this video, so we will explain those basic things. Yeah. So after we get a solution of a computing problem, the algorithm, solution, specifically the algorithm to solve that problem, so we need to estimate the amount of resource here, resource used. So this resource here pretty vague. So we want to provide more specific meaning to this resource. Basically, there are two types of resource. The first type, the primary resource, the most important resource. So that's the running time. The response time, the most important. It has the immediate impact to your, customers. If your customer happy or not, most of the time, it is determined by the response time. So we make it as the primary resource. Then there is a secondary resource. So that is the memory space used to solve this problem. Something you cannot see, it happens in the main memory in your computer, but it has impact also. Yeah. So the memory resource will affect your running time, the performance of your algorithm. Why? The reason is very simple. Your programs running inside the main memory, right? And inside the main memory, many different programs are running at the same time. Many different processes. So we call them processes. Running programs, so they are processes. So they compete for the memory resource. If your program uses too much resource, then, the memory resource not enough, so then those processes have to wait until, waiting for its turn to get a, memory resource. For that reason, if the memory resource is used too much, so overall, the performance, the running time efficiency, the response time will be slowed down. Will slow down. So that's the reason behind. But we say secondary resource because it will take effect, indirectly. It will, the result, the impact will build up, gradually, and eventually make your program running very slow. So in your algorithm design, definitely the first highest priority, try to reduce the running time. After that, next priority, reduce the memory space. All right. The methods used basically two methods, theoretical and empirical. So theoretical, so what we are doing in this class, theoretical, a lot of mathematical computation and get some conclusion from that work. But other than that, sometimes we also need to do empirical analysis. Empirical, okay, due to some reason. And in this section, later I will have one video to talk about this empirical analysis. Yeah. And for this class, we will do two programming projects. In those two projects, what do? Empirical analysis. All right. So then, efficiency of algorithms. So what do you mean efficiency of algorithm? Yeah. Regarding these two resources, two types of efficiencies. The first type we call time efficiency or time complexity. Yeah. So for different group of people, so they use different terminologies. Yeah. Some people, they call it time complexity, and some call it time efficiency. Yeah. Second, space efficiency or space complexity. Yeah. Here, so let's take a closer look at the space efficiency. Yeah. The amount of memory units required by the algorithm in addition to the space needed for its input and output. Why in addition to? The reason is very simple. First, the space, you need to use certain amount of space for input and output, right? So that's required part. For any computing problem, you need to store that part. So for that reason, we do not want to count it, because you always need to do that. So then we do not count it. So what do we count? The extra space used, other than storing input and output data. So for that reason, we call this in addition to. So that part. So we calculate that part. Then there is a special type of algorithms called in-place algorithms. Here, this in-place. In a previous video, I talked about the in-place concept, but here the concept is different. We both use in-place, but in-place, what in-place? That's different. In the previous video, when we talk about in-place, we talk about an element in an array is in place. So that's our, natural understanding. Compatible with our natural understanding, in place. Element in place. And here, when we say in place, we talk about some algorithm is in place. Some algorithm is in place. So the meaning is different. Its meaning is the extra amount of space used is bounded by a constant number. Bounded by a constant number. Extra space. We do not count input-output space. Other than that, you still need to use some extra space to manipulate your data. But that part of space sometimes could be pretty big. But we like to have some algorithms that we can put control on that extra space. We can put a control on it. So what kind of control? We use some constant number to bound it. Okay? So control the extra space cannot break the ceiling of that bound. Okay? Cannot. Has to be below this bound. So we'll put a control on it. If we can do that, then this type of algorithms are desirable. So we call it in-place algorithms. So this concept. All right. Next, related concept, input size. For the problem, your input data, there is a data size, right? So now let's look at the exact meaning of the input size. There are two different meanings. The first one is pretty obvious. Number of data items in the input. And number of data item. So usually we consider an array, right? Number of elements in an array. So that's the input size. Most frequently we use this understanding for the input size. But there is a second case. The magnitude of number n. Magnitude. The value, larger, smaller. So that value, magnitude of the number n. Also could be the input size for some special problems. So usually for special problems. Here, although when we use this, when we in this situation, we only need to work on one number. One number. Although it's a one number, but when this value is large, the problem could be very hard. So we use this number as the input size. Here, let me give you a special example. Checking primality of a positive integer n. Given a positive integer n, how to check if this number is a prime number or not? Primality check. Only one number. You only need to work on one number. It does not mean this checking work is easy. No. Actually, checking the primality is extremely hard. Extremely hard. Why? Because many people work on it, try to, using the current supercomputer. No matter how powerful the computer is, still it is extremely hard to check. Even some institute, some organization, use a lot of resource to do this in order to win a big prize. Because some agency, they gave a big prize. I remember 100,000 prize. Anyone who can break the record of the largest prime, they can win $100,000. Although not much money, but that means this thing is hard. Okay? And another evidence showing it is hard, there is the current encryption algorithm. Internet data encryption algorithm, RSA algorithm. Some of you may have heard of that. RSA algorithm was built on the primality of large numbers, or factorize one huge number. Okay, based on that factorization, then the encryption code, can be generated. Things like that. So you can imagine how hard it is. In that situation, the magnitude is the problem size. Later, so in this class, we will have a simple problem. In that problem, the magnitude is the problem size. What's that? Find GCD. GCD. You know that, right? Greatest common divisor. Find the greatest common divisor of two numbers. In that problem, magnitude of the larger number, two numbers, two positive integers, the larger one, that's the problem size. So here you can see we have some examples corresponding to the second case, input size. All right, next. So usually the larger the size, the harder the problem. Yeah. Natural understanding. Yeah. The size keep growing, so then the problems become harder and harder. Yeah. All right. Next, measure running time. Yeah. This one I mentioned a little bit in one of my previous videos, but here we try to understand systematically. Yeah. First, we need a scientific method to measure the running time. Yeah. Unbiased, okay? Objective, yeah. Reliable, stable way to measure. Okay? All right. So we need a stable measure for the running time. What do we need? Why? What do you mean stable here? Right? Yeah. It does not rely on the hardware computers. Yeah. Otherwise, it does not make sense. Someone, although has a slow algorithm but use a supercomputer, right? Someone has a better algorithm but use a very slow computer. How can you compare which one is better, right? Yeah. So that's not good. Yeah. So we need some special measure that does not rely on your computer, powerful or not, that kind of thing. Nothing to do with it. Yeah. All right. Another consideration, it does not rely on the quality of the programs. Some programmers, they can write very fast, very efficient programs. But some programmers without a lot of experience, so they do a lot of redundant, unnecessary work in their programs, waste a lot of resource and could be very slow. Yeah. So in that situation, we try to avoid that kind of programming skills related difference. Okay, yeah. So then the simple way we do, the main approach, use the basic operations in the algorithms. Basic operations. We can use many different operations, but we pick the basic. So what do you mean basic operation? How do you define basic operations? So we want to, give more description on it. Yeah. So the operation contributing the most to the total running time. Yeah. Some operations, although slow, but you only use it once or twice, not many times. So then you do not need to consider it. Yeah. So you consider the most frequently used operations. Okay. Yeah. So then if we identify those basic operations, we just count the number of basic operations used in the algorithm. Yeah. All right. So next, connect basic operations to running time. So if we have that, then we just use number of basic operations to indirectly reflect the running time. So that's good enough. Yeah. So that's our idea. Yeah. Identify the basic operation of an algorithm. How to identify, right? Yeah. So here, the common way to do it is usually the most time-consuming operation in the algorithm's innermost loop. Suppose we have nested for loops. In the innermost loop, which operation appears in the innermost loop. Okay, yeah, because that's the most frequently used operation. So then you compare, so which one has the biggest impact to your algorithm? Yeah. So with that kind of consideration, you can identify it. Yeah. Here, so let me give you some simple examples. Yeah. In our problem one, evaluate polynomial, definitely the multiplication is the basic operation. It dominates the addition. Addition only accounts for a very small portion. So multiplication dominates the running time. Yeah. Then find the minimum problem and a sort array problem. That's simple. Comparison. Basic operation. Right? Comparison. That's the most important, the most time-consuming operations in those two problems. Other than comparison operation, we also use assignment, right? Yeah. When you copy data, you do assignment. But you can see the assignment is less frequently used than the comparison. Yeah. Yeah. All right, so that's the 8.2. Yeah. So let me stop this video. Yeah.